Well, hi guys. This is a late Thursday night follow-up to our lecture earlier this evening. It's about 11 o'clock at night here, but I promised you I would get this done today. I think it'll be good to post up a couple of examples for you of what can happen in a 3 by 3 defective matrix case when you're trying to solve this linear system here. And I didn't want to waste any time getting this up for you. So I'm going to show you a couple of examples, kind of give you the idea of how this works. We did the 2 by 2 example in class, and I sort of indicated that usually the 3 by 3 example is very similar to how the 2 by 2 example works. So let's do this example here, and I'll show you that really is the case. All right? So here's a 3 by 3 matrix. And we want to solve this linear system. So we do the usual thing. We take the eigenvalues, which we're going to get by subtracting lambda from the main diagonal of our matrix. Okay, so we're going to do that, and this is what we're going to get. Okay, and the way to handle this determinant is definitely to expand the cofactor expansion along the middle row or column. Okay, so remember, it's not always the most obvious row or column. In this case, it's the middle row because you have two zeros here that I'm going to use. And so I'll have 2 minus lambda times the determinant of what I get when I cross off the middle row and column, which is just this 2 by 2 determinant on the outside. So it'll be 3 minus lambda times negative 5 minus lambda, and then plus 16. So I'm doing this fairly quickly, but it certainly is something that you guys want to be able to do. Okay, and the part that's in the bigger brackets here, the second term, I'm just going to turn that into a quadratic. I have lambda squared minus 3 lambda plus 5 lambda, that's plus 2 lambda, and then plus 1, right? Okay, and then this becomes 2 minus lambda times lambda plus 1 squared. And so the solutions are lambda equals 2, and lambda equals negative 1, and lambda equals negative 1. Okay? So that's my situation. Now, we don't know for sure yet whether this matrix is defective or not. We do have a repeated eigenvalue, so we should test and see whether or not this matrix is defective. So I'm going to look at the case of lambda equals negative 1 first, and try to look at the null space of the matrix that I get. We've done this many times. We just have to add 1 to the main diagonal, adding 1 because it's a minus 1 eigenvalue here, right? So we add 1 to the main diagonal, and we're going to end up getting something like that. Okay? The third row is obviously just a multiple of the first row. And what we're left with here is really, the middle equation tells me that, of course there's a pivot there, that y is equal to 0. And the top equation tells me that 4x plus 4z is 0. In other words, x and z are negatives of each other. Okay? So we're only going to get, and you can see here how the pivots are looking, we're only going to get one free variable, right? So the one free variable being z, and I'm going to use a 1 for z. That means x would be negative 1, and y has to be 0. So there is my vector, my one and only vector that I'm getting that corresponds to lambda equals negative 1. Okay? So here's where, we can write down one of our solutions. One of our solutions to our linear system, then, is just going to be e to the negative t times negative 1, 0, 1. All right? That's the first solution, just in the usual way, right? E to the lambda t times v. So I've just simply written that down. Now, to get a second solution, I'm going to come back over here again. Let's not forget we have another lambda equals 2, that we're going to have to do as well. But I want to keep working on the first eigenvalue, the negative 1 eigenvalue, because at this point we know that the matrix is defective. And I need to come up with a second solution. So remember the form that we talked about in class. It's e to the lambda t times w1 plus t times w2. And our job is to choose w1 in such a way that when I apply a minus lambda I to it, I'll get W2. And if I again apply a minus lambda I to that, I'll get 0. Okay, so let me just remind you of the picture here. This is the way that you want to think about it. You're going to choose W1 in such a way that when I apply a minus lambda I to it, I get the second vector W2. And when I apply the same matrix a minus lambda I again, I've got to get 0. Okay? So we need to calculate a minus lambda I, which actually, if you think about it, is just this matrix. This matrix right here is, in this case, lambda is -1. So that is the matrix A plus I, right? A minus lambda I is just that matrix. Okay, so I need to find a vector W1 that survives this matrix, but does not survive the square of that matrix. So I'm going to take A plus I. I need to actually square that matrix. So it's going to be 4, 0, 4, 0, 3, 0, -4, 0, -4 times itself, right? So we just some good old-fashioned matrix multiplication here. Okay, I'm multiplying A plus I by itself, and what I'm going to get when I do that, let's see, we have to calculate this whole thing. I'll do this quickly because I know you guys can check me on this. I'm going to get 0, 0, 0, and then 0, 9, 0, and then 0, 0, and 0. Okay, so in the 2 by 2 example that I had done in class, you might remember that when we squared the matrix A minus lambda I, we got the 0 matrix. So here we did not get the 0 matrix. So we have to be a little careful. Because remember what W1... W1 has to survive the first matrix, A plus I, but not survive the second matrix, which is this one right here. Okay. So you have to think about what would be a vector that would not be killed by this matrix, but would be killed by this matrix. And a good choice, you always want to try and pick something that's simple. And a simple thing to choose that will work, and I'll explain why it will work in a second, is 1, 0, 0. Okay. The reason is that if you do that, then W2 becomes, what is it, 4, 0, 4, 0, 3, 0, -4, 0, -4, applied to 1, 0, 0. If you do that, see what happens is this calculation is going to pull off the first column of the original matrix, right? The first column of the original matrix. Notice that the vector that we got is just a multiple of the eigenvector that we had found earlier. So that is something we should expect, because W2 right here, the last vector before it's going to get killed on the next power of A minus lambda I, that is an eigenvector. This step right here, the vector you get is definitely an eigenvector. Okay, so we have W1, we have W2. We need to make sure that W1 is killed by this matrix, so that if we did it twice, it would be killed. Well, you can see the first column of this matrix is 0, 0, 0. So if you multiply 1, 0, 0 onto this matrix, even though there's a 9 in the second entry here, in the second row, second entry, this vector is only going to fill the first column, which is all zeros. Right, so this vector W1 is going to work out really, really well. And so what we're going to get, let me write down what our x2 is going to be. x2 of t is e to the negative t times W1 was 1, 0, 0, plus t times W2, which was 4, 0, -4. Okay? So those are my two solutions that correspond to lambda equals -1. All right, now there was another eigenvalue. I'm going to erase this. You can always rewind the tape if you need to. But there was a second eigenvalue, and I want to carry this problem all the way out to the conclusion. So if we look at lambda equals 2, we have to find, now this one's going to pull its weight because it only showed up with a multiplicity of 1, but we still need to find the eigenvector, right? So I'm going to subtract 2 from the main diagonal of this matrix, and I'm going to get something like that, right? Okay. You know, you're going to cross off the second row here, and what you're really going to notice pretty quickly is that it's the second variable that is going to be totally free here. So the x and the z, if you take this little system, I won't do the EROs, but you could very quickly do them. X and z have to be 0, right? But y is free, so it could be t. So my vector v in this case would just be 0, 1, 0 after I bust out that t, right? Okay, so my third solution would be e to the 2t times 0, 1, 0. So that is it, okay? So now, let me just write down the final answer, and then I will be happy with this particular problem. So the final answer would be C1 times the first solution, which is e to the negative t times negative 1, 0, 1, right? Plus C2, e to the negative t times, what do we have here, 1, 0, 0, plus t times 4, 0, negative 4, plus C3 times e to the 2t times 0, 1, 0. Okay? That's it. Not too bad, actually. The choice of W1 right here, there's more than one choice you could have made, right? So there's other things you could choose, and so therefore you might get an answer that looks different than mine based on what you chose, right? In the same way that, you know, how you choose, you know, your eigenvectors in the first place, there's more than one choice for an eigenvector. But at the end of the day, the family of solutions, which is what this general solution captures, that whole family is the same regardless of what choice that you made in the first place. Okay, in the interest of keeping the video short, I'm going to stop this clip and make another clip to show you another situation that can happen for a 3x3 defective matrix. So again, this case that we just saw right here was the case where we had two different lambdas, right? And the one that was repeated only gave us one eigenvector, right? So it's kind of like a mixed case, a mixed eigenvalues. Let me show you another video. I'm going to make another video where we have the same eigenvalue 3 times, okay? And let me know, stop by and ask me any questions if any of this isn't clear.